All right, people. We're going to be talking about Charles's law. Now, Charles's law is the relationship between volume and temperature. So, how does the volume change when you change the temperature? One of the best examples is a hot air balloon. And the guy who came up with this equation, what is his name? It was a French name. It was let me see it. Jacques Charles. I don't know if whatever his name is. Jacques uh, ja, Charles. Charles is. So what Charles did is he was the first person I think to go in a hot air balloon, but he figured out the relationship between the volume of a gas and the temperature of the gas. So let's say you have a regular sized balloon and normal air, not hot air, normal air. But then you come and you bring in a little fire, a little bit of heat. All right. So if you add a little bit of heat, the balloon is going to get a little bit bigger because the particles inside it now begin to crash into the walls a little bit more, right? They crash into the walls a little bit more, and it causes the balloon to expand. Now, if you increase the heat even more, right? So I'm trying to increase heat. All right, so we increase the heat even more. Well, the balloon is going to get larger too, and the particles are going to crash inside the wall more and more and more, and they're going to push the balloon upward. It's going to get some lift. So that is how the hot air balloons work. So how did he come up with this equation? Well, the relationship is between volume and temperature. And you can show relationships through math, right? So the volume isn't equal to the temperature, but the volume changes depending on the temperature. So depending on how much you change the temperature will change your volume. And that word I said, depending on how you change the temperature, that's the proportionality constant. The temperature would change at a certain ratio. The volume would change at a certain ratio depending on how you change the temperature. So the relationship was, well, the volume is equal to some number times your temperature. Well, this worked for any volume, right? This worked for any volume. So it worked for a different volume. We'll call that volume 2. And then it's still the same letter B. It still had that same ratio. And then it had at the second temperature. So we have T2 and V2. So completely different temperature, completely different volume. It still had that proportionality constant. This value, this number that kept repeating regardless of the data point. Just like how the Boyle's law had that K, this one has a different constant. But if you rearrange both of these equations, right, if you have it now B is equal to, and we'll say this is, let's get rid of that T, let's divide both sides by T2. So divide by T2 to both sides. And then it's going to cancel here. Boom, boom. And sorry for my ugly writing, but B is going to equal V2 over T2. All right. Now, if we do the same thing over here, except for the sake of simplicity, let's call that V1 and T1. So that way we know first and the second. The formula, after rearranging it, is B is equal to V1 over T1. So there is this ratio now with volume. As the temperature goes up, the volume goes up, right? The balloon expands as you increase the temperature. So since both of them always had that same ratio, well, you can set them equal to each other, and your equation, well, let me delete this. You leave out of here, balloon. We don't need you. And we don't need all this junk anymore, do we? We just need our equations. Yeah, that's what we did. All right, so we don't need the box anymore. Get out of here, box. We don't need you. Get out of here, box. We don't need you. And now we have that V2, that they're basically the same thing, right? They're both equal to B. They're both equal to B, so we can set them equal to each other. And now this is your gas law, and this is how you can compare or predict the different volumes at different temperatures. That's what's really, really important about this, is you can predict different volumes at different temperatures, even some that you can't achieve. And I'll tell you why that was important. But all right, let me get rid of these boxes. They're distracting me. They look kind of like a book. Okay, I'm gonna delete. All right, so to make calculations easier, to make them easier, this is how I write the equations. But so it's V2 times T1 is equal to V1 times T2. All right, so for some reason, kids don't like to divide. They get scared with fractions. So simplifying it to this way is fine too. The way to simplify it, if you've forgotten your math, you multiply both sides by T1 and then multiply both sides by T2. So the T2 is going to cancel, and you don't need to ask your math teacher. All right. Now, how do we use this in a problem? Let's do that next, okay? Let's do that next. Let's go. All right. Now, how do we use that equation? Oh, I should have brought it with me. Bring it with you. Bring a friend. All right. So, a sample of helium gas at 20 degrees Celsius and 300 milliliters occupies a volume of 450 milliliters when heated to an unknown temperature. What is the final temperature of the gas in Kelvin? Now, we cannot use degrees Celsius. We cannot use degrees Celsius in this type of equations, because if we go back to this equation, what if we use 0 degrees Celsius? What if you use 0 degrees Celsius right there in any one of those? Get 1,000,000 divided by 0. Don't do it. You'll get in trouble. All right. You can't do it. You can't divide by 0. So 0 Celsius is actually really, really bad. So we got to turn this into something called Kelvin. So to turn it into Kelvin, we got to add by some magic number called 273. I'll explain to you where we got that number from in just a moment. So to convert degrees Celsius to Kelvin, so Kelvin is equal to degrees Celsius plus 273. So since we have 20 degrees Celsius, we have 293 Kelvin. All right, so that's our temperature. And I like making a little list. So I'll stop writing in red. I'll call that V1, T1, V2, and T2. I like grouping the numbers at the bottom so that we can so that we can stay organized. All right, so we can stay organized. I'm not a very organized person. I'm very messy, so I need some sort of list. All right, so over here we have 300 milliliters as our first volume, so we're going to put that right here, 300 ml. Now right here I didn't write my unit. You would fail me. You would be like, dislike on this video. All right, right here, volume 2, 450 milliliters. Now some of you are saying, why don't we have that 0, Mr. Sanchez? I know someone was going to call me out for this, so I had to change it. Now, do we have to turn it into liters? That is a good question. If your units match, it doesn't matter what your units are. All right, if they match. It's good practice to use liters. That's standard practice, but it don't matter. All right, we're looking for temperature, and we don't know it. So we don't know our second temperature. So let's put that in red right here, so we'll look for it. T2. Ugh. Oof. Oh, someone's sending me messages. So make sure now we just plug and chug, as they used to say. I don't know if you guys hear that anymore. All right, T1 is 293 Kelvin. And then V2 is 450.0 milliliters. All right, so how do we get T2 by itself? Well, right now they're being multiplied, so we got to do the opposite. Let's divide by 300. Divide by, and I know some of you are always like, yo, why do you keep saying you got to do the opposite? Because you'll remember. And you'll never forget. You will never forget. So now you got to do the math right here. Multiply the top, divide by the bottom. All right. How do we do this? How do we do this? So I'm going to do 450 times 293 divided by 300. I know some of you put the point zeros in your calculator. Don't do that. You don't need to. But now we got 439.5, and then this was Kelvin. So take a look at the units. See how you have a milliliter and you have a milliliter? That's why they didn't matter, because they cancel out. The only unit you got left is K. That's what we're looking for, Kelvin. Boom. Now, if you got Kelvin and you want to go to degrees Celsius, subtract 273. And that's it. Now, I'm not going to do this problem. You're going to do it on your own. But what I want you to see is there's a very, very important whatchamacallit from your text. Hello. Here we go. You get out of here. All right. So, I want to talk about this. This is in your book. And this graph explains why we use 273. Whoops, wrong one. Whoops, wrong one. It's so late in the video, Mr. Sanchez. How? Quiet you. All right, here we go. All right, here we go. So this graph is really important. If you read the text, as you should all be reading it. Always read the graphs. If you read anything, read the graphs. Read what it says under the graphs. Try to understand what it says. See the problem that goes along with it. It will improve your skills drastically. Por favor, do it. All right, but let's take a look at this. I don't know much about these. I don't know anything about those, Mr. Sanchez, but I know water. All right, so let's see what it's saying. So water's right here, and look at the data points. You see those dotted lines, and then right here, not a dotted line. Okay, so let's think about what that is. Well, let's go down. It's 100 degrees Celsius. Well, what happens to water at 100 degrees Celsius? At 100 degrees Celsius, water turns into a gas. So this is a data point where you can study the gas laws, right? So water can only be studied there. All right, methane, CH4. Methane becomes a liquid at whatever temperature this is. It's a little bit above negative 100 degrees. I think it's like negative 79 or something like that. I don't know. I'm guessing. All right, but where the solid ends is where it becomes a liquid. So everything else is real data points. Everything else is real data points. So the person that used this information was only able to study this part. But since there was a pattern, this pattern, right? Since there was that pattern, they made a straight line. They did what's called extrapolating. Extrapolating is where you see a pattern and you put a graph that goes along the exact same point, and it follows the same trajectory. So even if you can't do the experiment or you can't do the calculation, because you know the pattern so well, you'll be able to predict other aspects of it. So they did these with all these different gases, and they all converge to the same point. No matter what gas it was, it always went towards the same point. It was a theoretical point. All of them kept going to the same place. Well, what temperature was that? That temperature was negative 273.2 degrees Celsius, also known as absolute zero. Absolute zero is the point in which no particles, absolutely nothing moves. There is zero energy. That's what Kelvin tells us. Kelvin is a measure of energy at zero, or particle motion, right? Or kinetic energy. If you have zero movement, you'll be at absolute zero. Now, that temperature has never been reached. I believe we've gone to like it's like 10 to the negative 13 like decimal place. Like it's 0.0000. It's close. But the reason why it can't move is because there's even smaller particles than protons, neutrons, and electrons that are consistently moving. There's also another thing that we're going to learn in the upcoming chapters about something called the uncertainty principle. It basically kind of limits our understanding, and it's kind of like there's a lot of information on this. It gets crazy. It gets interesting. But anyways, the whole point of it is that there's zero movement. There's zero movement. It gets super, super cold. It's perfectly still. There's a tangent. There's a theory that black holes are their gravitational pull is so massive. It's so massive that it sticks particles perfectly still. It makes them perfectly still, and if they're perfectly still, they're super, super cold. So you'd expect a black hole to be this crazy hot ball of energy, because it is on certain parts. But there might be portions of it, like the center, like the core, where it's super, super cold. I don't know, man. Science is crazy. I still don't get it, man. I still don't get it. Anyways, sorry for the video being so long. I just wanted you guys to understand where 0 Kelvin came from. What else? I wanted you to understand Charles's law, but you guys got this. That's a piece of cake. Where Charles's law came from and how it's used. But piece of cake. Take care.